So today we're going to take a look at a concrete Cython Plus program. We're here in a Cython Plus environment in which, so it's a Python virtual environment in which we have installed Cython Plus, and we have already downloaded the Cython Plus standard library and the Cython Plus actor runtime. We can immediately get our program, which is called sign file tree, which you can find in the same project as the Cython Plus runtime and the standard library. If you need to reach this step again, please refer to our Getting Started video. So this program, which is called sign file tree, given a root directory, it walks all the files in the directory and the subdirectories recursively. And for each file, it collects its metadata, so size, permissions, stuff like that, and produces a hash of its contents. And the idea is that we can run the program at boot time and compare it to a previous run to see if the system has been tampered with as a way to implement a secure boot strategy. Let's immediately compile the program. Like this. And I'll start by running it once to show you what it does. So I just pass a string directly to Python like this. And this will run the program. So what the program does is it outputs a JSON representation of all the collected data. And so here we can see each file and directory it traversed. So we see the README of the directory, and the source code file. And by default, we didn't give any argument. It takes the current directory, so it ran in the current directory. So given this is a Git directory, we also have all the Git files. And we have the files generated by the compilation of our source code. And this is a normal JSON representation, which can be loaded as a JSON object, turned into a Python dict, and stored, analyzed, whatever. Yeah. So let's take a look at the source code for this. Here it is. So as ever, we must specify that we compile towards C++, because this is required for Cython Plus. This is all, this header stuff is all things that can be seen in previous videos, like the Getting Started video. We specify that we need the FMT and crypto library. So the FMT library is needed for as a backend for the string formatting library of Cython Plus. And the crypto library is needed for the hashing library. Yeah, and we need to specify them here to be sure we have both. Usually, if you use only one of them, it's automatically resolved, but when we have several, we need to specify them all at once in one place. So now we fetch the needed types from the actor runtime, also list, string, the formatting utility of the standard library. And we also fetch the hashing library in the standard library and the OS module, which provides some OS functionality like reading the entries in the directory, reading a file, writing to a file, opening a file, stuff like that. So also some convenience constants for the current directory, the parent directory, and the path separation character. And then we have some constants that are used for formatting the output into JSON. So this is how we format the output when we have a file. So the name of the file will be here. The output of the hash will go here, and the stats will go there. Same thing, except without hashing for a directory. For symbolic link, we add the target, and we produce the JSON for the statistics here. So essentially, we are formatting JSON strings by hand because Cython Plus doesn't have a JSON library yet. But this is simple enough to do it by hand. So now let's get into the meat of the code. So we initialize a scheduler here, which will be used to run the actors. And then we have our first actor class, which is actually a base class. It's called node, and it represents any node in the file tree. So essentially a directory, a file, or a symbolic link. It has a path. It has the output of an object, subclass object representing the output of the stat system call, so the metadata associated to the file. And it has a string called text, which will hold the formatted output representation, so the JSON that will be then printed to the console for this specific node. So when we initialize it, we need to initialize the queue that would be used by the actor system. This is, again, entirely customizable by the user, which is why we need to specify it here. But we can just use the queue type, the batch mailbox. So the mailbox type provided by the actor runtime in this library. And then we also initialize the path and the stats, given the stats. And then we have some essentially abstract methods to build a node. So this will be run asynchronously to build many nodes in parallel. And then once you have all the nodes built, and this includes having their JSON representation computed, we will call the write node method, which will be called synchronously, and just walk all the tree and output all the JSON for each file into a big JSON object. So we include the utility here to turn the stats into their JSON representation. So we reuse the string we saw above, this one, and just output format it with all the necessary fields. So that way we only have to write it here and can reuse it everywhere else. And also we have this static method, which is essentially a constructor for a node, which takes a path and computes the stat system call for it, and based on the results determines if actually it's a symbolic link or a directory or a file. And those are the subclasses of the node class, which we'll look at in an instant. One thing here is that this string takes an ISO qualifier. So this is because the type system in Cython Plus does not include notion of immutability yet. And we need to prove to the compiler, because the type system still wants to make sure that everything we do is thread safe, that it is thread safe to use each node as an actor with its own data. So essentially this path will be given to the node we're about to build, and we need to prove that this node cannot be no internal state of this node can be modified from the outside. So essentially we need to prove that this node is the only way to access the string of the path. This is not actually strictly necessary because the string is supposed to be immutable anyway, and so it doesn't matter if many threads can read it at once. But there is no way to express this conveniently in the type system yet. So what we do instead is we do what we would really need to do if the string was mutable, and make sure only the actor can access it. And this is why this is an ISO string, and why we consume it here, and so that we can then consume the node and make sure it's the only way to access any of its internal state. Yes, so that's it. Then we have the directory node. So the directory node takes a list of actor nodes, which will be its children, so all the entries in the directory, so nodes for each the subdirectory or file or symbolic link in the directory. And the interesting part is here, so we use the system call, we use the call in the OS module lister, which under the hood does some system calls to fetch the entries in the directory. And then, so we have some basic checking here of not null. It's also because the exception system in Cython Plus is not yet complete. And so many primitive calls prefer to return null instead of raising an exception, because the exceptions currently all require the GIL, and so this way we need to do it by hand, but we don't need the GIL even when there is an error. So anyway, we get the entries, we look through each entry, we avoid the current directory and the parent directory, so otherwise we would just loop forever. And then we build the path, the full path of the entry relative to the path of the directory. We create a node for it, and we turn this node into an actor, so an active node. So for more information on this, please refer to the Introduction to Actors video. But this essentially makes sure that the node is the only way to access any of its internal state, and then turns it into changes state to an object that is only interacted with asynchronously. So all the method calls become asynchronous, and it starts behaving like an actor. Then we compute the JSON representation for the directory. So essentially, we just need to fetch the formatting string we wrote above and give the path and the JSON representation of the stats of the directory. And then, and here's the recursive part, for each actor node that is a child of this directory, we will tell it to asynchronously build the node, so the JSON representation and etc. For this node. So this may be a subdirectory for some nodes, so it will do the same thing, or it may be a file, and we'll look at that next, or a symbolic link. And then once everything has been computed, so in a separate phase of the program, we'll call the write node method, which will write to a given output stream the representation of the directory itself, and then the representation of each actor child. And so you notice here what we do is we empty the children list, and we pop in turn each item, which is so far considered well as an actor, so it behaves like an actor. Then we consume it. So this only works if the actor doesn't have any work to do. So if it's done, we consume it and turn it back into an object, standard object that is interacted with synchronously. So this is essentially still the same object. It's just we change how we interact with it, and by using the consume keyword, we check that the actor won't still be used as an actor after we turn it back into a synchronous object. And then once we have a synchronous object, we can just directly call the write node method on it synchronously. So this is a standard recursive call as opposed to here, which is an asynchronously recursive call. So this call will probably finish before the recursive node is built because it's built asynchronously. In this case, we wait until all the child nodes have written their stream to exit this call. So this is a standard synchronous recursive pattern. Anyway, now let's look at the file node. So what we do when we find a file. And so the file has, so in addition to the data from a standard node, so a path, statistics, text representation, it also has two strings for the hashes we will compute, so SHA-256 and SHA-512. Otherwise, the initialization is pretty standard. And then what we do with this file is we open the path and then use the hashing library in the standard library to get a hash object for both algorithms and read the file in chunks and update the hash with this chunk. So we don't need to have read the whole file to produce the hash. We can update the hash with the first chunk of the file and the second chunk of the file and so on until we have read the whole file. And the output will be the same as if we computed the algorithm on the whole file. This is a property of how hash algorithms work. And this should be familiar to anyone who knows the Python hashing library or even C hashing libraries, because it works the same. So we update the hash with the chunk in question. Once we're done, we can stop, or if there's a problem while reading, we can stop as well. And then we close the file and compute a hexadecimal representation of the hash for each hash. Notice that so far we do a lot of error handling a bit by hand, so all these null checks and these two booleans are there to do this error handling. Again, this is because Cython plus exceptions so far are actually Python exceptions and they require the GIL. So it means if and when an exception is triggered, the GIL is acquired. And this would, well, probably it won't happen in the standard case, but if it does happen, it will slow everything down because several threads would try to acquire the GIL simultaneously, potentially. So since what we want is not to report an exception and crash the program, but actually handle it and just say, okay, we had an error while reading. We want to do this in a way that doesn't use the GIL, and so we do it by hand. Yeah, so it's still pretty simple, but future versions of Cython Plus will try to have a better exception system. Anyway, then when we have computed the hashes, we produce the JSON representation of the node in question, of the file node. So we use the path, but also the hash representations. If the hash failed for some reason, or if we couldn't read the whole file or anything happened, we just print an error string instead. And also we use the JSON representation of the stats again. And then the write node method is really easy. It's just write the JSON representation to the output stream. So this is in the second phase. You'll notice that we do the formatting of the output string, of the output JSON component, so to say, in the asynchronous build node call, and not here in the write node method. We could do it in the write node method, but the asynchronous build node methods will be run in parallel. So this means we can format strings in parallel for each node. Whereas if we did it in the write node method, it would all happen sequentially. So we would use we would make a worse use of computational resources if we did it here. In this way, we can take advantage of the fact that it's in parallel. Then there's the symlink node. So when you have a symbolink link, all it has is a target string, and this is really easy. What we do is we use the OS module's readlink method to get the target of the symbolic link, and we then format the output JSON representation using the formatting string shown above, and the path, target, and the statistics. And same as the file, the write node representation method just writes the JSON representation to the output stream. And then we have essentially our main method, the most thing that runs everything, which takes a root path, computes the node for this root path, builds the node. So here it's a synchronous call because it doesn't need to be asynchronous. It will just happen here synchronously, but presumably the root node is a directory, and so its own children will be computed asynchronously. And then we wait until all the asynchronous calls triggered by this call, so all the children and descendants of this root directory have finished building. And so once this is done, there is no more work to be done for any actor. And so we can call the write node method on the root. First we print some essentially beginning and end for the JSON representation, so that it's a full JSON representation without any missing bits. And then you can call the write node method on the root. And this is safe because remember the write node method for the directory will turn the actors, children of the directory, back into synchronous objects. And this only works if there is no more work to be done for the actors. But this is the case because we call it scheduler.join. So everything is fine. And this is it. We just, from Python, when we call this from Python, we just release the GIL and call the method, and we can get some bytes representation of the root directory from Python. By default, we take the current directory. So this is it. it's in fact pretty understandable, and it works. Um, I can show you the output, for example, of the parent directory. So if we run this on the parent directory, we will also scan what's in the parent directory, so the standard libraries and the runtime system. Oopsie. I need to use single quotes because of the double quotes here. And bytes, because it expects bytes. And there we have it again, same thing. So this time the root was the parent directory, so we see the stuff in the sign file tree directory, but also, if we go back far enough, stuff in the standard library, like the string formatting code, etc. So this is it.